Right, okay, good evening everybody. My name's Tom Williamson and my talk this evening is on the scientific method. Okay, now I think it's very important to teach the scientific method because of what it's brought us. I don't need to tell you what science does. We get things like space travel, discovery of things like the structure of DNA, vaccines, eliminating whole diseases, and of course the technology that allows things like the internet. All wonderful, all moving the world forward. Now, rejection of the scientific method brings about things like homeopathy, belief in the supernatural, bit of Derek there, the anti-vaccination movement. I was expecting a few boos there actually, but never mind. Thank you very much. And a particular passion of mine, creationism, represented by someone's car there, saying the fossils say no, which of course they don't anyway. Okay. So what do we use the scientific method for? Well, obviously we use it to acquire new knowledge about the world and about nature. But arguably, more importantly, we also use it to test previous knowledge and, where necessary, to correct it. Okay, so I don't know what everyone's scientific backgrounds are. There may be a few professors in here, a few doctors who probably won't need the scientific method explained to them. So in order to help me out, in order to give me an idea of what people know about this, I'm just going to put in a few scientific terms on screen. And if you think you could tell me what they are, I'm not going to ask anyone, but if you think you know what they are, just raise your hand. Okay, first one's a law. Who thinks they know what a law is? Scientific law. About half, about half. What about theory? Scientific theory? Bit more, okay. What about prediction? A little bit less. Not too many more of these. Experiment? Okay, nearly everyone. And the last one, hypothesis. Very good. So I'm speaking to a very educated crowd. Okay. Well, it could be lies, could be lies. Okay. So how is the scientific method carried out? Well, the first thing you've got to decide is what you're going to study. And to this end, you'll start off by doing your background reading, make a few observations, and maybe formulate a question that you're going to answer. So the first part, the part following on from doing your background reading, is making a hypothesis. And a hypothesis, boiled down as far as I can boil it down, is a statement that's falsifiable. And when I say falsifiable, I mean that you can do something to show that your hypothesis is false by experimentation. So on a very basic level, something like mixing chemical A and chemical B will give chemical C. That's a fairly straightforward hypothesis. So once you've got a hypothesis, you then devise an experiment. And the experiment is there to test the hypothesis. And that's where you change one variable, keep everything else constant. So you'll have your control and your same experiment with your changed variable. And you've got to have more than one possible outcome. So once you've devised your experiment, you need to come up with a prediction. And a prediction is the outcome of the experiment if your hypothesis is correct. So after you carry out the experiment, you compare your results to the hypothesis. And if your result matches your prediction, then you've got reason to accept your hypothesis. But if it doesn't, then you have to either reject or refine your hypothesis. So taken together, the whole process is have your hypothesis, generate an experiment, and come up with a prediction. And if your prediction matches the result of your experiment, then you've got reason to accept your hypothesis. If it doesn't, then you've got reason to reject it. And once you've got many hypotheses, they all come together and you explain them with a theory. So a theory is something that explains hypotheses. And once you've got a theory, you have to test it. A theory, you should be able to generate many more hypotheses from it. And if you go on to test these hypotheses and you have reason to accept them, then that strengthens the theory. However, if you generate hypotheses that are rejected, then you've got to ask yourself a key question. Can the theory be modified? If it can, then great, you've got an improved theory. If it can't, you have to reject the theory and try and come up with a new one. But either way, science moves on. So the last part of the scientific method which I'd like to talk about is a law. And a law is basically a statement of relationship between elements that must hold true under given conditions. Now, to me, I find laws pretty boring because they don't explain anything. You know, they're just there. And for example of a real law rather than the law of similars or infinitesimals. What's the other one? Succussion, isn't it? Anyway, that's a little bit of a sidetrack. Would be E equals mc squared. So to sum up the whole process, start off by doing your research, come up with a hypothesis, test hypothesis with experiment. Then you have to confirm, reject, or modify your hypothesis, come up with theories that explain the hypothesis, generate new hypotheses with the theory, test these hypotheses, then modify theory as you go, and so it goes on. And you might devise a law along the way. Now, how is this done in practice? I'm going to explain, very briefly explain what quality controls are involved, how science is communicated, and the peer review process. And for anyone who's ever been through the peer review process, it's kind of tough. You have to go through a metaphorical gauntlet to get a paper accepted. So this is what happens. You start off by conducting a study, and you write a paper where you explain your hypotheses, theories, etc. And you then submit that paper to a journal. And if they like it enough, your paper will get reviewed anonymously by 3 reviewers. And then it can go backwards and forwards between the reviewers and yourself. And that can take many months before your paper is accepted eventually. So when you have a paper accepted to a respected scientific journal, it'll end up in a database called PubMed. Now, for any of you who ever use science, this screen should be fairly familiar to you. This website, ncbi.nlm.nih.gov/PubMed, you know, the people who came up with it were really keen to make it memorable. Anyway, that is burned in my brain. And it's the first place to go if you ever want to find the primary research literature on a subject. So if you're debating on the internet and someone sends you a link and it starts with NCBI, etc., then it should be a peer-reviewed study and it should be a pretty good starting place. And once it's in there, then it's a chance for other people to review your work, repeat your experiment, and if it gets repeated all over the world and your hypothesis is accepted, and you've got a very strong hypothesis,